All right, welcome. Let's do some more polar area practice. So this is going to be BC Homework 10.4, the extra practice for BC Homework 10.4. And the first kind of problem I said, just like find the area of each of the regions. And so I'm going to do them separately, right? And so for each of them, I'm going to start off, and I'm going to test, drawing a radial line from the origin to the edge of the region. And this one's kind of tough to tell on A. But at each point, I am going to be going through both curves. And G is on the outside and F is on the inside. Okay, so I know that area of region A is going to be equal to 1/2 of the integral from, oh, wait a second. I don't know what the bounds of integration are going to be. I need to figure out where those intersection points are. And so, you know what? I think I'm just going to do that right now. Okay. Let's just do that work off to the side in gray. And I'm going to just say, where do the two things equal each other? Now, in general, finding polar intersections, if you were in class, I told you it's really not a world you want to get into. But for now, we are just assuming r is always positive and theta is strictly between 0 and pi. So we're not going to have any of those like kind of false intersections, or not even false, but just hard to find intersections. And I'm just over here, I'm factoring. Doesn't make sense. Theta minus 1. And that gives me theta equals 1 and theta equals 3. Okay, so I know that right here, I've got theta equaling 1, and I know that right here, I've got theta equaling 3. And both of those seem pretty reasonable. I know that 1 is close to pi over 3, and 3 is close to pi, and both of those things are happening. So I'm going to clear that out. And now I'm going to be ready to find the area of region A. Okay, that's going to be equal to 1/2 of the integral from 0 to 1, right? Because over here is where theta is 0. Up here is where theta is equal to 1. And on the outside, I have g of theta. So I would say g of theta squared minus f of theta squared, because f was on the inside, d theta. Okay. I think in this video I'm just going to be setting up the integrals and not evaluating them, because if you need to see me take these all the way through, just go watch the regular homework video. I did every one on the calculator, and and there's lots of Math 9 usage there. So that's going to be the area, or the area of region A. Yeah. For the area of region B, if I go and I reach out from the origin to the edge of B, I'm only ever hitting one curve, right? It's just that curve that I'm hitting switches after theta equals 1. So I know that, I lost my little point for theta equals 1, but that's all right. I'm going to say for region B, area is going to be equal to 1/2 of the integral from 0 to 1 of this, I'm still in the shot, this curve right here, and that's f of theta. So f of theta squared, there we go, d theta plus, okay, after that, it picks up on that curve, okay, and that's g. So I'm going to say the integral from 1 up to the y-axis, we know that's pi over 2. I'm integrating on g of theta squared d theta. And that's how I would find the area of region B. For region C, I'm going to be strictly between theta equals 1 and theta equals pi over 2. But when I go and I reach to the edge of C, I know I'm hitting the curve twice, so I know I'm going to need to use subtraction. Okay. So this will be equal to 1/2 of the integral from 1 to pi over 2 of, okay, on the outside, I've got f of theta minus on the inside, I've got 1/2 of the integral from 1 to pi over 2 of g of theta squared. Okay. And now I could combine those into a single integral like I did to find the area of region A, but I'm just going to kind of switch back and forth because both of them are equally valid. And I want you to understand that it's the same thing using integral properties. region D is going to be more of the same, right? Because if I draw my radial line from the origin out to the edge of D, I'm hitting two curves. So I know that I'm going to have 1/2 of the integral from, but this one's going to go from theta equals pi over 2, the y-axis is what's splitting C and D, all the way to theta equals 3. So I got pi over 2 up to 3. On the outside, I've got f of theta, that's this curve, right? And so I'll have f of theta squared minus, on the inside, I've got g of theta. So that would be g of theta squared, d theta. And that would be how I would find the area of region D. Now region E, when I draw my radial line, I'm just only hitting one curve. But you got to be careful. After the intersection, you can barely even tell. But over here, when I go out there, I'm hitting F again. So it's going to be G, and then it's going to be F. Okay, so I'll get rid of those. I'll say, okay, E will be, all right, I'm going to start out going from pi over 2 up to 3. And that's g of theta. And then after 3, and I have to write this as two separate integrals because I've got different bounds, right? I'm going to say that's going to be, this pen's a little too thick, I think. That's from 3 to pi of, went back to f, so it's f of theta squared d theta. And the last one, to find the area of region F, that's going to be, I mean, it's so small you can barely see, but if I went to the edge, I would be hitting both curves. So I know that I'm going to be subtracting two integrals, and I'm going to have 1/2 of the integral of what's on the outside. It's this curve right here, and that was g, right? So g's on the outside. Minus f was on the inside. And then my bounds will be starting at 3 and going up. Okay. And that's how I would find the area of region F. Okay. Now the next few are like, well, let's combine two of them and write them as one integral. And so that's a different type of question. So it's going to say, all right, write one integral to represent the sum of areas B and C. It might be easiest for me to actually just draw this. I'll give you my own sketch. It's this, right? It's that whole thing. And this is f of theta all along. So what I feel like I should be able to do is just start at 0 and just integrate on f all the way up until pi over 2. Yeah. And I think that's going to be the way to go. Okay? So I'm going to say that this area is going to be equal to 1/2 of the integral from 0 up to pi over 2, pardon me, of f of theta squared 1/2 r squared d theta, right? Okay, that's one integral. Now, I know I didn't ask this one on the official worksheet, but this is just as good of a question, right? One integral to represent the sum of areas C and D. And we can do that, right? Because what we really want is just, if I can do that. Stroke, yeah, there we go. Okay, I want that whole area. And so if I wanted to do that, it's going to be an outside minus an inside, and so it would be 1/2, and if I needed it to be one single integral, I'm going to be integrating from theta equals 1 up to theta equals 3. On the outside, I've got f of theta. Oh no, that was the actual worksheet. Okay, and on the inside, I've got g of theta. And then that would be one integral that would represent the sum of areas C and D. Yeah, f squared minus g squared, because g's on the inside. And now, if I wanted the area of regions D and E combined, well, that's all the way over in the second quadrant, so I probably don't need to draw a whole bunch of places where x is positive. That's really just going to be, if I track it, it's just inside that curve, which is f of theta. So if I want, this amount of area, I'm going to integrate. This is one where they might not give you the bounds of integration, right? So I'm just going to integrate over the whole second quadrant, which is from pi over 2 to pi. Okay, so I'm going to say that this is equal to 1/2 of the integral from pi over 2 up to pi of, it was just f, so 1/2 r squared d theta. And the last problem I've got for you is the sum of areas E and F. How can we write that as one integral? And so we're just going to say, well, again, this is all over here in the second quadrant. But this is where I'm just following curve G from pi over 2 to pi, right? So if I was to find this amount of area, and that's good enough, then I will want to integrate again from pi over 2 to pi. This time 1/2 r squared is 1/2 g of theta squared d theta. And that's all for this set of practice problems. I think this was good. It's a good variety of just like kind of direct area between two curves, area where you have to add two integrals together. It just kind of had all of the varieties. And I think if you've done this and you've done the official homework, you have practiced enough polar areas, and you just be confident in your work. So thanks for watching.